We're talking about dimension, and we made the definition that the dimension of a vector space a finite dimensional vector space is the length of any basis for that space. And that immediately, of course, gives us a number of the properties that we wanted from dimension. Well, that it corresponds to the length of a basis for the space. Gives us that, this vector space, this sort of canonical vector space, tuples of n field elements has dimension n, because we know a basis for it, which has that length. And the last thing that we wanted was that it was a sensible size. It behaved like volume or area. It behaved like cardinality in the sense that we could use this inclusion-exclusion type principle. If I had two spaces to measure the dimension, I should hope to be able to measure the dimension of A, add the dimension of B, and subtract the overlap, like we did for area and for volume. And so that's for cardinality, and so that's the theorem that I want to give the proof of. Suppose U1 and U2 are subspaces of a finite dimensional vector space. Then this formula holds. The dimension of U1 plus U2, which is the smallest vector space containing the union of U1 and U2, is equal to the dimension of U1 plus the dimension of U2 minus the dimension of the intersection. And in that sense, behaves just like cardinality or volume. So the proof, we postponed until today, and the proof uses our new definitions of dimension and basis, as it has to, because we're using dimension, and it uses this notion of extension. Right? So one of the other things we did last time was to say that given an independent set, a linearly independent list, we can extend it to a basis, and given a spanning list, we can reduce it to a basis. And we'll use that in the proof. So we first consider the vector space U1 intersect U2. So U1 and U2 are subspaces of a finite dimensional vector space. We can take their intersection, that's a vector space. And it's also finite dimensional because it's a subspace of a finite dimensional space. And it has a basis. We don't know what the basis is, but let's just write some symbols to represent that basis. U1 vectors U1 up to UM. That's our basis for U1 intersect U2. Now let's give it a name. For convenience, B, U1 intersect U2, the basis of the intersection. So what's the dimension of the intersection? terms of the other symbols on the board. We don't know it as a number, but what's the dimension? M. The dimension is the length of any basis for the vector space. Okay. So we have this basis, and U1 intersect U2 is a subspace of U1 and a subspace of U2, right? That's what it is by definition. And so we can extend by our extend independent. A basis is a spanning list which is linearly independent. In particular, it's linearly independent, and we can extend it to a basis of this larger space that is contained within it. So this B1 U1 intersect U2 can be extended to a basis of U1. And that basis will be, well, it'll start out the same vectors, U1 up to UM, and then we have some additional vectors, V1 up to Vj. What's the dimension of U1? How long is this list? M plus j. That's right. Okay. Similarly, we can extend this basis of the intersection to a basis of the other space that it's a subspace of. And that one would start out the same way, U1 up to UM. And then we need some new vectors, new symbols, W1 up to WK. And what's the dimension of U2? M plus K. Okay. So now we want to make a basis of the sum and count it. Claim U1 up to UM, the common starting point, and then the V's, V1 up to VK, Vj, sorry, and then the W's is a basis of the sum U1 plus U2, the smallest vector space containing the union of U1 and U2. Okay, so to be a basis, it needs to be two things. It needs to be a spanning list. So it needs to span this space, and it needs to be independent. Right? Those are the two things we need to check. It's a linearly independent spanning list for U1 plus U2. Well, the spanning part is easy because U1 plus U2 by definition are things that can be written of in the form U1 plus little u2, with U1 in U1 and little u2 in U2. Well, everything in U1 can be written as a linear combination of this first m plus j vectors. Everything which is in U2 can be written as a linear combination of the U1 up to the UMs and the W1 up to WK. And I'm allowed to take sums inside the space which is the span of this thing. So therefore, anything I can write in this form, I can write as a linear combination of these vectors. There's going to be a little overlap, right? I write an expression for that, I'm going to get two copies of this one. Okay, so great. So the span works. And so the main thing to show for this to be a basis is that it's linearly independent. So how do we show something's linearly independent? That's often something that causes a moment of panic. We have a couple of tools so far. We have the definition, and we have this linear dependence lemma. Right? So we're just going to use the definition. So you don't know how to show it. One thing you can do is write an expression for 0, and then show all the coefficients are 0. And that proves that the list is linearly independent. So let's write an arbitrary linear combination of the vectors u, v, and w equal to 0. So that would be the sum from I equals 1 up to m, ai ui, so coefficients ai, plus the sum from, say, L equals 1 up to j, BL, VL, plus the sum from n equals 1 up to k, Cn, Wn. So that's an arbitrary linear combination of the vectors in our spanning list that we'd like to show as a basis. And our task is to show that all the coefficients are 0. AI equals 0, EL equals 0, Cn equals 0 for all I, L, and N. Okay, so if this is true, this is what we're sort of starting with. We have to rearrange this to try to find some reason why these coefficients should all be 0. One thing I can do is to separate it. So I'll take this to be on one side of the equality, and I'll move this and this over to the other side. Cn, Wn. I'm going to omit the indices just to avoid crowding the board. Is the sum of the ai ui's minus the sum of the AIs minus the sum of the BL, VL. Okay. So we had two bases that we agreed on and one basis that we're trying to show. The U's and the V's were a basis for one of the sets, right? The U's and V's were a basis, then they spanned U1. So that means this whole expression here is in U1. The WNs appear in the basis for U2. So this whole expression here is in U2. And that means we're dealing, and these two sides are equal, so that means we're dealing with something which is in both U1 and U2. So the sum of the Cn WNs, or of these, is actually in the intersection of U1 and U2. And we have a basis for that. And its basis is U1 up to Um. That means we can write a new expression for CnWn. The sum of the CnWNs, and here it goes from 1 up to k, is equal to some linear combination of the U's, because the U's span the intersection. So let's say I equals 1 up to m, d sub I, u sub I, for some coefficients di in the field. Because this is a basis, right? So now we have a new expression for CnWn. And we have a new expression for 0. And this expression for 0 takes place entirely as a linear combination of U's and W's. And the U's and W's spanned u2. Right. And we're a basis for u2. In particular, the linearly independent. So therefore, all the di's must be 0, and all the cn's must be 0 by definition of linear independence. So that gets rid of these, right? These are all 0. This expression. That means that our big linear combination simplifies to sum of the ai ui plus sum of the bl vl and again the u's and the v's, u1 up to um, v1 up to vl was a basis for u1, in particular a linearly independent set. And so the fact that we have an expression for 0 means all the coefficients that appear in that expression must be 0. And so in fact, all the coefficients that appear in our expression are 0. That's what we needed to show. So this u1 up to um, v1 up to vj, w1 up to wk is linearly independent. And since it was spanning, it's also a basis for u1 plus u2. Okay. And the last thing to do is to do the dimension calculation. Which now is just arithmetic. So what's the dimension of u1 plus u2? In terms of our letters. How long is this list? How long is this basis? Just have to add 3 numbers. M, J, K. It's M plus J plus K, which I can rewrite as M plus J plus M plus K minus M. This is to match up with the basis for U1. This is to match up for the basis for U2. And we've double counted M. That's dimension of U1 plus dimension of U2 minus the dimension of the intersection, U1 intersect U2, which is the basis we started with. Okay, so that proves that. So I want to summarize what we know so far. And we'll stop there, and then we have some review and a connection to direct sum next time. A basis is a linearly independent list of vectors in V that spans V. That's a basis, well, a basis for V. If V is finite dimensional, every basis V has the same length, which we call dim V. Every basis has exactly that length. And in this case, a linearly independent list has at most n vectors, at most dim V vectors. And can be extended to a basis of V. That extension might be trivial if it has exactly n vectors and it's linearly independent and it's in V, then it's already a basis of V, and so we need to add nothing. But okay, it can be extended to a basis of V by including new vectors that I've chosen appropriately. And a spanning list for V is at least dim V vectors and can be reduced to a basis of V, in this case by choosing vectors to throw away. Last thing I want to do is to connect it back to direct sum. Suppose U1, big U1 up to big UM are subspaces of a finite dimensional vector space V. Suppose further that V is equal to the sum of U1 up to UM, comma here, and the dimensions work out. The dimension of V is equal to the dimension of U1, adding all the dimensions together up to the dimension of UM. Then in fact, V must be the direct sum. This is a unique, nice description of V. The proof is very easy. The idea is that you choose a basis for each UI. Concatenate them to make one big list of all of them, which has length. We concatenate them, we get a list by this that spans V. And by the second part, it has length dim V, so it's a basis. And then you use the characterization of direct sum. The characterization of direct sum that says that the expression for 0 is unique. Maybe I'll give the details of that next time we talk. Yeah. Just write one after another. It's the non-commutative addition, the monoid operation for lists.